Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for generating combinations. Let's look at the problem description. We are given two integers n and k, and we have to return all possible combination of size k from the range 1 to n. We can return those combinations in any order. Let's take a look at the example 1. The n is 4 and k is 2. So we have to generate combinations from the range 1 to 4, and each combination is of size 2, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. These are all the valid combination of size 2. And also one thing we have to notice, the combinations are unordered. So 1, 2 and 2, 1 are same. They are not unique. Okay, we have to keep that in mind. And in the case of example 2, n is 1, k is 1. The expected output contains a single combination. The constraint for these problems are the n is ranging from 1 to 20 and k is ranging from 1 to the value of n. Let's look at the approach to solve this problem. So we are given this input, n is equal to 3 and k is equal to 2. The expected output is the combinations 1, 2, 1, 3 and 2, 3. As we read in the problem description, combinations are not ordered. So 1, 2 and 2, 1 are same. 1, 2, 3, 3, 2, 1 are same combination. So in the final output, either one of them needs to be included, not both. So let's generate the combinations manually first. Okay. So the given input number n is 3. So the range of values that we can use for generating combination is 1, 2, 3. Okay. To begin with, we have an empty slice. Next, we want to have a combination that starts with each element in the input set. So we include 1 in the first combination, 2 in the second combination, 3 in the third combination. Once the number is included, we cannot include that number again down the line. For example, here in the next level, we include 2 and 3. Okay. So 1, 2 and 1, 3. And next, for this case, we should not include 1 because the 1, 2 is already generated. If we include 1 here, it will become 2, 1, which is equal to the combination 1, 2 because the combinations are unordered. So when we process this number, we have to include the numbers which are greater than the current number. Okay. So that's why we include only 3. We are not including 1. So we get only one combination out of in this path. And when we come to 3, this is the last element. And because we cannot include the numbers which are lower than this number, we will not have any combinations generated out of this path. In this level, we get the combination of size 2. So whenever we see the combination size is equal to the value k, then we have to include that in the final output. So 1, 2, 1, 3, 2, 3. These 3 combinations will be included in the final result, and that is an expected output. So at every level, we have to initialize the starting number which can be included in the combination. Okay. So when we begin here, we say number 1 is the starting number. So we include from number 1. So 1 will be added to first combination, 2 will be added to the second combination, 3 will be added to the third combinations. So from here, when we go one level down, we increment the current number, and that will be the starting number for the next level. For example, in this case, we increment 1 and we say starting from number 2, we can include the rest of the numbers in the input set into the combinations. So from here, we included 2 and 3. And for this number, when we go to the level 2, we say starting number is 3 because we are incrementing 2 and declare that as the starting number for the next level processing. So starting from 3, we include the numbers in the input range. So that is the last number. So only 1 is getting added. Okay. Basically, as we go down, we reduce the input set. Okay. And also we keep track of the number of elements in the combinations generated so far. Once the size of that combination is equal to k, then we add that to the result. So when in this level, we get the combinations of size 2, which is equal to k. So we add these 3. We can see a hierarchical relationship between these partial outputs. Okay, we can view that as a tree. So if you see here, to begin with, n is 3, k is 2, empty slate, and the starting number is 1. So we include the numbers in the slate into the slate starting from number 1. For this call 1 is included, for this call 2 is included, for this call 3 is included. And then from here we increment the current number, which is 1, and declare, and we can set the current number plus 1 as the starting number for the next level processing. So the start number becomes 2, and from here we include starting from number 2. Okay, here 1 comma 2, 1 comma 3, and in this case we increment the current number, which is 2, and set that as a starting number for the next level processing, so it becomes 3. So in this case only 3 is included into the slate, right? So when we generate the combinations recursively, as we go down one level, we increment the current number and set that as a starting number for the next level processing. And also in each level we decrement the value of k. Okay, so from here it is k is 2. When we come to level 1, we decrement k is equal to 1. When we come here, k is equal to 0. So the moment we see k is equal to 0, then we add the slate slice into the final result array. So from we include this, and here k is equal to 0, so we include this. Here k is equal to 0, we include this. So that's what I listed here. Basically we can use the recursion with the backtracking to solve this problem. So basically this is a combinatorial enumeration problem, and we can easily solve this using recursion. First we initialize the slate with the empty slice of int, and initialize the result with the empty slice of int, and we initialize the starting number with the value of the first number in the input set, which is 1. Okay, and then we keep track of the number of elements to be included in the slate using k. So we each level we go down, we decrement the value of k. Basically we make a call to a helper function with the input number n and k, and then the current starting number and the slate and the result. Okay, so if the k value is equal to 0, that means we generated the combination of the required size, so we add that to the result. Otherwise, for each number in the range from the current starting number to n, we make another recursive call which increment the current number and set that as a starting number for the called function. And also we decrement the k value, and we pass this partial slate and the result. So we repeat this until all possible combination of size k is generated. Let's look at the flowchart. Input for this combined helper procedure is variable n, k, start num, slate, and result. First we check whether the k is equal to 0. If so, we have generated the combination of the required size. So we create a copy of the slate and then add that copy to the result slice. Otherwise, we initialize the index with the value in a start num variable, and then we enter the for loop. Here we check if the index is less than or equal to n. If so, we make another recursive call passing the variable n and k minus 1 and idx plus 1 and then updated slate. The slate includes the idx and then the result variable. We repeat this until idx is greater than n. Once it becomes greater than n, then we break out of the loop and then return the result. Let's move on to coding. First I initialize the result slice, which is a slice of int, and then the slate, which is a slice of int. Then I make a call to the combine helper function and I'm passing the value of n, k, and then the starting number as 1 and then the slate and the address of result. Then finally I return the result. Next I'm going to implement the combine helper function. First I check whether the value of k is equal to 0. If so, I create a copy of the slate and add that copy to the result slice and return from this function. Otherwise, I initialize the index I with the value of start num, and this loop runs until I is less than or as long as I is less than or equal to n, and then I make a recursive call to the combine helper function and calling n and decrementing the k value and incrementing the current index value so that the current index will not be included in the further recursive calls, and then append the current index to the slate and then result. Next I'm going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. Let's do a code walkthrough for this input. Value of n is 3 and the value of k is 2. The expected output is 1, 2, 1, 3, 2, 3. So in the combine function, first we initialize the result slice to empty slice of int and the slate variable with empty slice of int. Okay, and then we make a call to the combine helper function with the value of n, k, and then the starting number 1. Okay, and when that combine helper function is called, here first we check whether the value of k is equal to 0. In this case it is 2. So we go ahead and initialize the index variable for the for loop. So in this case the starting number is 1. So this loop runs 3 times starting from 1 to 3. Okay, so in each iteration it calls the combine helper function again with the value of n and the decremented value of k, which is now k becomes 1, and then the current index is added to the slate so that we can see the slate contains the value 1. in the first iteration. In the second iteration, the slate will contain 2. The third iteration, the slate will contain 3. Okay. So in the first iteration, when this function is combine helper function is called again, we check whether the value of k is equal to 0. In this case, it is 1. So we go ahead and initialize the index with the starting number. The starting number is in this case 2. Okay. So we make another recursive call to the combine helper function with the value of n and the decremented value of k. In this case, the k becomes 0 and then the incremented value of the current index. So it becomes 3. Okay. And then we append the current index to the slate. So current index is 2. So that gets added to the slate. Okay. And when this function is called, it checks where the value of k is equal to 0. The moment it sees value 0, it creates a copy of the slate and then add that to the result slice. So the result slice now contains 1, 2. Similarly, in this iteration 1, the index value is 3. So the 1, 3 is added to the result. After these two combinations are added to the result slice, the control comes back to this function. So the first iteration in this function is completed. The second iteration, it includes the number 2. When this function make a recursive call, it includes the number 3 into the slate and decrements the value of k. So the k becomes 0. The moment it sees the k equal to 0, it adds the 2, 3 to the result slice. When this is completed, the control goes back here and this make another recursive call to include the number 3. Okay. So 3 is the last number in the input set. There won't be any more recursive call made. So the control comes back here and finally comes here, and the result array contains 1, 2, 1, 3, 2, 3. So that is an expected output. Next, I'm going to do the time and space complexity analysis for this solution. The time complexity for this algorithm is order of n factorial divided by k minus 1 factorial times n minus k factorial. Let's see how. Okay. So for the case 1, the value for n is 3 and the value for k is 2. Okay. We can compute the number of combinations of size k that can be generated from n elements using this formula: n factorial divided by k factorial times n minus k factorial. Okay. And then for each combinations, how many append operation we are doing? We are doing k number of append operation, right? For example, here k is equal to 2. So we are appending for this combination. We are doing 2 append operations. 1 is here, 1 is here, and 1 is here, 1 is here, 1 is here, 1 is here, right? So for each combination, we are doing append operation that is equal to the size of k, right? So that's why we are multiplying the number of combinations with the value of k. So k times n factorial divided by k factorial times n minus k factorial will give us n factorial divided by k minus 1 factorial times n minus k factorial. This is the total number of append operation. So this is the computation we do in this algorithm, appending to the slice, correct? So for this input, the number of combination is equal to 3. 3 factorial divided by 2 factorial times 1 factorial, which gives us 3. We have to multiply this by the size of the combination, that is 2. So 2 times 3, 6. We get the total number of append operations for this input is 6. And for this case, the number of combinations is 6 and the number of append operation is 6 times 2, 12. Right? So the time complexity for this algorithm is order of n factorial divided by k minus 1 factorial times n minus k factorial. And with respect to the space complexity, we need to allocate space of size to accommodate k elements in the slate. Okay, so at any point only one path is active. Okay, so the space complexity is the size of the each combination, that is the value of k. So that is why the space complexity is order of k. Thanks for watching this video. Have a great day.